Welcome everyone to the IEA Bioenergy webinar series hosted by the Canadian Institute of Forestry. My name is Ronnie Huang and I'll be kicking off today's session. Today is June 20th, 2018, and we are very pleased to have Henrik Thunman and Freddie Tengberg with us today, who present on GoBiGas, an industry-relevant state-of-the-art reference for advanced biofuel production via gasification. We are also very pleased to have the task leader of IEA Bioenergy Task 33, Kevin Whitty, who will be opening up this session and introducing our speaker for today. To start things off, Kevin Whitty is a professor of chemical engineering at the University of Utah and leader of IEA Bioenergy Task 33, which focuses on promoting and disseminating information about gasification of biomass and waste. And with that, I'd like to pass it over to Kevin.
Thank you, Ronnie. I'm happy to welcome everybody to this webinar about the GoBiGas biomass to biofuel demonstration system. This is being hosted by IEA Bioenergy. The GoBiGas system, which was built by Göteborg Energy in Sweden, is a demonstration system that represents the world's largest ever plant for production of substitute natural gas from biomass. It's a very ambitious project that has helped advance bioenergy technology deployment. Today's webinar, as you see, is being jointly presented by Professor Henrik Thunman, who's the head of the Division of Energy Technology at Chalmers University of Technology in Gothenburg, Sweden, and Freddie Tengberg, the site manager for the GoBiGas project. Both Henrik and Freddie have been deeply involved in the GoBiGas project and know the technology and operation history really well. The presentation is expected to last around 30 or 35 minutes. After the presentation is complete, there will be an opportunity for the audience to ask Henrik and Freddie questions. To keep things orderly, rather than having everybody sort of ask all at once, we will ask that questions be typed into the chat window that will become available after the presentation is over. The presentation is being recorded and will be available online at the IEA Bioenergy website, which is just ieabioenergy.com, after the webinar is over. The presentation slides that Henrik and Freddie will be showing will also be available on the IEA Bioenergy website as a PDF file. With that, I think we can start the presentation. So Henrik and Freddie, please begin whenever you are ready.
Thank you, Kevin. Good afternoon, good morning, good evening, everybody. I am Freddie Tengberg. Let's see if we can switch slides here. Okay, here we go. GoBiGas is, as Kevin mentioned, the first plant in the world to produce high-quality biomethane from biomass via gasification technology. It is also the first Swedish plant to inject biomethane into the national natural gas grid. In Sweden, it's a very modest grid, but still, we are the first plant to inject into it. Initially, the project was meant to be of 100 megawatt capacity, but it was later decided to switch it into two phases, where first step would be a 20 megawatt plant. It was meant to be a demonstration plant to test the technology, to test also the commercial basis for building a larger plant. And then as a second step, build an 80 to 100 megawatt biomethane plant. The first demonstration plant was never meant to be profitable as such, but the combination of the two was meant to be making good business. The performance goal for the demonstration plant, to see if that was something to build on, was an energy efficiency of biomass to biomethane of at least 65%. It was intended also to have a total biomass to energy efficiency of 90% or over, and to run for 8,000 hours continuously each year. We demonstrated during the operation the first goal of 65%. It was almost reached. We were at 63%, giving good indications that this was definitely achievable. The biomass to energy was also close to its goal, and we never ran long enough to run for 8,000 hours continuous operation. However, we have good indications that that was definitely achievable with several rounds of running 1,600 hours continuously, repeatedly. I will take you very quickly through the technology of the plant. We will go into more detail of the most important parts of the technology later. But the blue line and arrow here indicates the path of the biomass through the gasifier, turning it into process gas and being refined until it finally becomes biomethane, or green natural gas, if you like. The black arrow is the flue gas train. So let's start here with the blue line. After the gasification, which is done in a fluidized bed gasifier, we cool the gas and then remove particles of tar and heavy hydrocarbons. Later on, removal of light tar, making the process gas ready for the methanation unit. The methanation technology consists of several steps. Basically, what it amounts to is removing sulfur and CO2. We have before we go into the actual methanation reaction, we also have a pre-methanation to recover as much heat as possible because of the high energy efficiency of the plant. It's optimized in several ways to reach the 90%. Finally, the gas is dried and compressed before it is fed into the national grid. It turns out that to build a commercial, it is required to have more than one gasification unit. This is due to the maintenance interval proved to be between 12 to 18 months. This is very similar to what is normal in the forest industry. Whereas the methanation unit has a longer period of running before we have to have a maintenance shutdown to it. It's around 48 months, very similar to a petrochemical industry. In fact, the technology is similar to a petrochemical plant. And the commissioning period of the methanation unit was only 3 weeks. We anticipated 4 weeks. So the technology is very robust and easy to start up. The gasification technology needed more tuning and understanding. And this is why the conclusion is that when building a commercial plant, we need 2 or possibly even 3 gasifying units to feed one methanation unit. As the plant was built with great financial contribution of the Swedish Energy Agency and the rest funded by Göteborg Energy, the major partners for gasification were Metso and Repotec. Metso is now Valmet, and Metso Valmet acquired the technology license from Repotec of Austria. This part was done as a turnkey plant through an EPC contract. It was sort of delivered in one piece. The methanation, however, for the methanation, I should say, the technology was delivered by Haldor Topsøe of Denmark, and Göteborg Energy acquired that technology itself. It was engineered by Jacobs process in Holland through an EPCM contract, meaning that they manage the engineering, the procurement, and the construction of the plant. In a commercial situation, the ideal solution is to buy everything from one supplier. This supplier then subcontracting the whatever partners are required. This was not possible in a first of its kind solution. This is why it was done like this.
Okay, then now we come to the technology. Now my name is Henrik Thunman, I will go through the gasification part. And the gasification part, that more or less as indicated, was the part that was not really commercial at the state, but also to make it, we couldn't buy 100 megawatt unit. So when the choice of the gasification technology became on this indirect gasification system, where you burn on one side and produce the heat for the gasification. And the technology chosen was delivered from the Gissing plant in Austria. It was the first generation. The second generation of this type was built in Göteborg, where they also introduced the drying. It was proven that it was really important to get this technology working. And then the commercial side of this type of technology, what it is intended for the heat and power production, has been built in Senden in Germany, which is a 50 megawatt unit. And that is up and running and actually run on commercial ground. This technology was at the same state and was upgraded in Gothenburg to 32 megawatt unit. And this was then going for more than 100 megawatt sizes. But to go to 100 megawatt sizes, actually the second route of the technology development, which was partly done here at Chalmers, where you add on a gasifier to an existing boiler. It has been done also by IHI in Japan, in Yokohama, and they also have been demonstration unit in Kuyan, Indonesia. So this upper route here is also actually going for the 100 megawatts, taking advantage of the development of fluidized bed boilers, not actually just this upscaling with this technology. It's mostly done for smaller scale. So if I look at this technology, so this also, the building of the gasifier at Chalmers was also part of it, the handling the uncertainty of the gasification. So that was built in 2007 and was complemented by several reactors at lab scale. So this plant has been run for more than 25,000 hours, providing them training for the personnel and also research results that made it possible to operate the demonstration plant. The demonstration was in 2014 up, and it was finalized according to the board of Göteborg Energi in March 2018, and it's now mothballed, this plant, and waiting for the right commercial conditions. And the commercial side is actually cancelled at this stage. So looking on the technology, as I said, it's based on the circulated fluidized bed. It's a regular boilers. We have several hundreds of them, and if you look in the world, there are several thousand of these boilers up and running. It's a regular circulated fluidized bed where you have a heat carrier, a bed material that even out the temperature in the boiler system. You take in the fuel, you heat, convert it and produce the heat. Part of the bed material heat the bed is leaving the furnace into the cyclone and separated back. And then you have the flue gases going through a heat convection path and the filter system before it goes in the flue gas. So if you are going to build a dual fluidized bed of a commercial size that this is the intention of this project. And you actually have one of the circulated fluid bed boilers. And to confuse a little, I turned it upside down, but it's actually giving you a little easier how they are connected. And then you connect it to the bubbling fluid bed boiler with the difference that they don't have recycling. So it's the same. You have the fuel feed, you have the boiler, you have the convection paths, you have the filter system, and some condensation before it goes out in the chimney. To build a dual fluid bed boiler, you connect these two. So the bed material that is heated and separated in the cyclone is transferred to the gasifier, and the fuel that is fed to the boiler or to the gasifier is converted as far as possible, and then the char that is not converted is going into the combustion chamber, producing the heat for the process. To do this connection, you need actually to dry the fuel. And the drying is extremely important. To get the high efficiency of this, you have to dry the fuel as far as you can. And this is, the further you can dry it, the higher efficiency you get. If you put up the system like this, it most likely will operate for some hours. And that is due to the fact that the gas coming out of the gasifier will have a lot of large tar molecules that will plug the cooler. So one of the important parts, and which is the really development that is done in the demonstration, is actually how to control the chemistry. And this is done by taking the fine particles leaving the gasifier, which is soot, tar, and also chemical compounds like the bed material and alkali components and other things. You take it into the combustion side where you regenerate the system, and it's actually attached to the bed material again. And it's actually going with the bed material into the gasifier. It releases its catalytic component, getting the gas quality right. So this is the second loop. I will go through it a little deeper in the next slide. But this is the key part of the process actually to get it to work that we have discovered during this project. And that is the chemical components that you have to balance is the calcium, potassium, and sulfur. Another part is how to get the polaromatics, what we can call the tars, but actually tars with very few rings, so they're not clogging. These are also then usually burned in the boiler, but you can also see them as product if you can take them out in a good way. If you look back on the chemistry, how we actually operated the gasifier, and what we was discovering was that we artificially had to control the sulfur and potassium inlet onto the combustion side, and how to circulate them with the external cycle. By doing this, we actually could control the tar levels and the quality of the gas. And that we could do by having the methane concentration in the raw gas as indicated. So in this picture to the right, you can see the tar concentration as function of the methane concentration. And the different colors are different fuels. So each fuel has its own line. And you have an upper bound, and that is the line which is giving what the cooler could stand before it gets clogging. So if it went on the right side of this, we had to add potassium and sulfur to the system to get down the gas quality into the right window. But we should be very careful. If we get into too much potassium into the system, we start to produce potassium carbonates, which would clog the cooler, and that clogs the cooler even faster. So what you want to do is that you want to keep just below the line, which is of the design for the cooler. And in the GoBiGas, you can take the gas down to around 140 degrees without getting any tar clogging on the surface. And this was actually developed very far in the system. And the last run, which was operated for 1,850 hours, and that was a chain in the fuel feeding system was broken. showed no indication of any clogging or any problem on the chemical cycle of the process. So actually what we can see that during the 3 years, more than 3 years that we operated the plant, we actually learned how to control it and also artificially to balance the chemistry in the process. If you look on the performance of the gasifier, we usually take the mass balance, or we have taken the mass balance of the gasification unit. So to guide you through this picture is that if you take in 100 megawatts of wood pellets into the gasifier, you provide also heat from the boiler and steam. And this will convert the wood pellet. And you will produce some methane ethylene, around 30% of it will be that. 50% will be the syngas. You have carbon dioxide, which represents that you have to separate it in a methanization step. You have the charcoal, that is the heat provider. You have the light hydrocarbons, like benzene, toluene, and selenium, around 3%. And then you have the larger polyaromatics, mainly naphthalene. And if you sum this up on the chemical side, you go in with 100 megawatts of chemical energy and go out with 102.5. And it should be a little more if you didn't have the oxygen transport between the rest. To make the process to work, of course, we have to take part of this, mainly the charcoal, back into the boiler, burn it, and produce the heat for the process. And if you take the methane, which goes to the synthesis process, which is around 81 megawatts, or 81% of the fuel, and you get around 6% as the hydrocarbons. At the present, this was burned on the combustion side, but in overall, one can look on the chemical efficiency of this process around 87%, which is actually meeting these targets that was put up in the beginning. If they go to the really tricky part, which is actually connecting the gasifier with the methanization, which was really the part of it undeveloped at this stage, or also can have some modification, and that is the conditioning. And this is in the GoBiGas, it was the RME scrubbing to take away the longer hydrocarbon, and the carbon beds that took the lighter hydrocarbon. The carbon beds was a really last-minute design, and it was a big effort during several years to get this up and running in a way that we could reach the 20 megawatt output of the methane. The RME scrubber is an extremely expensive part, which also needs to be modified because the RME is much more valuable than the methane coming up. And it turned out with the design and the quality demand that you had to add twice of the RME than design. So this is something that needs to be modified. But looking on this, you actually can get it up at the high quality of the BTX coming out here, making it as product, and not necessary to burn them in the combustor. If you can find another way to remove the longer hydrocarbons, it could be, these can also be products. And part of this project, we actually tested self-cleaning plate heat exchangers. And these pictures in the top show a picture of the heat exchanger, and the lower part is some calculations. But what it actually showed was that the quality of the gas leaving the gasifier, it was possible actually to condense out the hydrocarbons on plate, and it would work. Given the fact that one can use boiler systems, one can also look on the boilers that we have in our system. And this is, if you look on the gray part here, and it is circulated through the bed boilers installed in Sweden, and blue is bubbling through the bed boilers. If one takes advantage of these and add a bubbling bed to circulated and vice versa, and look on the potential in Sweden, it actually would be able to produce an enormous capacity of biomass gasification in existing infrastructure. The potential in Sweden alone is around 35,000 megawatts of biomass gasification if one can take advantage of the boilers that are installed. And this is also what we show with the demonstration, that this would be possible. It also designed, and also we look at several evaluations on having electric fuel production. And we have Statoil coming and looking on the possibility to have an electrolyzer to actually convert the carbon dioxide, not separate it, but instead convert it by hydrogen from the electrolyzer into the SLG production. Due to economic, it was not possible, but it turned out that it was very much feasible technically. It was not a big thing. So even this demonstration gives some idea what electric fuel production would cost and how it could be designed.
So now, how much did it cost to run this plant, this demonstration plant? This is the area of operation where we use wood pellets as the feedstock. And then the operational cost was just over 900 Swedish kronor per megawatt hour. That converts at 90 euros per megawatt hour, or approximately $100 per the same megawatt hour. However, with the identified improvements of the existing process, the wood pellets would come down quite a bit. The cost of running with wood pellets would come down quite a bit. And the long-term intention was to run on forest residues, which would bring the cost down even further. And I will get to the recovered wood. With the identified modification of when building a new plant, further improvements were of course possible, and that would take the cost with forest residues as the feedstock to around 60 euros per megawatt hour, or $67 for the same thing. If using recovered wood, the cost would be 40 euros per megawatt hour, or let's say $44. However, using it with recovered wood would need new environmental permits. But we had a permit to test it, so we saw that it is certainly feasible to do it. Recovered wood or forest residue would be the preferred feedstock. And this all happened with the staffing costs, the personnel costs, representing some 20 euros per megawatt hours as, let's say, an overhead of this, because the plant was run as a standalone unit. Had the second portion of the second phase been built, they would be run from the same control room with the same staff, so it would be brought down considerably. And if it was shared with more plants, it would be even reduced further, so that this offset would not be part of the cost, which it is now. This graph shows with the full personnel costs at this level. So, if you were to build a new plant, what would be the most economical size? What capacity should it have to make the most financial sense? We have calculated this using the exact production costs of the different components of the plant, and applying scale factors such that, to build a twice as big vessel doesn't cost twice as much. And we used this component by component to calculate the investment cost. And it turns out that the best alternative is around 200 megawatt output plant. If you go further, the cost savings are not significant, and you introduce other problems related to the infrastructure of receiving the feedstock, etc. So it turns out that the investment cost when you are at 200 megawatt capacity is around or less than 3 euros per megawatt.
Okay, and also to compare this to other systems that are up and running, we wanted to compare it with a commercial heat and power plant. And the dots you see here is the cost for installed heat and power plants in Sweden during the last 10 years. When you go to smaller scale, you always take, make, they have not had the same efficiency, they have not the same fuel flexibility and so on. But when you come up to scales around 100 megawatts and above, the technology-wise are very similar. And the difference in cost is mainly due to local conditions and local conditions and timing of your investment. This is the uncertainty due to factors which are not technical. And looking on this, and you can say that as a rule of thumb, a biomethane plant of a large scale is the double of a regular heat and power plant. And the uncertainty is not really into the technologies, other uncertainties that is always connected to this type of project that is a big thing. So if I sum this up and look at the cost, what would it cost them to produce on a commercial unit? We calculated them for a 20 megawatt plant, taking in the development that they're seeing, and look at the capital cost, including interest, development cost that we say that we need to have certain development time, operational cost based on the figures that we get, feedstock based on forest residue. We ended up with a total cost around 1,300 Swedish crown per megawatt hour, which is corresponding to 117 euro cents per liter gasoline equivalent. If we increase to 100 megawatts, it decreased dramatically. It boosts investment, but also the operational cost because we have the same personnel. And it's then down to 65 euro cents per liter gasoline equivalent. And the preferred site that we identified then was the 200 megawatt SNG output, and then we are down to 53.6 euro cents per liter gasoline. And this is for forest residue quite expensive. If one build the first plant and operate it for recovered wood, this will be getting down then to around 35 euro cents per liter gasoline equivalent. But that is of course a very limited feedstock. So if you go for big scale, this is more likely to be the range that are in there.
So to conclude, we built a demonstration plant that met the criteria and demonstrated that this is feasible technology. It is ready for commercial implementation. We learned how to control the gasification process, as Henrik has described, to find the window where you can safely operate the gasification for a long period. We could not reach financial break-even with today's market conditions, and therefore the plant is now mothballed, waiting for the right conditions before it is started up again. So with that, we thank you for your attention, and we will be happy to take your questions.
So thank you, Henrik and Freddie. At this time, what we will do is open up the webinar for questions from the audience. If you have any questions for Henrik and Freddie, please type them into the chat window, and I'll steer the discussion from there. I also note that there is a one-question poll, which you should be able to see on the screen, which we would ask you to complete just regarding your professional field. We use this information to better understand the composition of the audience. So if you have any questions, go ahead and type them into the chat window. Let's see. So I see that there's a question that just showed up from Pavel that says, maybe I missed that point, but at what market conditions, break even, would a 200 megawatt plant fly?
Am I being heard? Yeah, it would fly when the gas is the market price for the gas is around 44 euros per megawatt hour.
60. Around 60 euro per megawatt hour.
Yeah, sorry, 60, yeah.
Okay, thanks. Next question is, if the mass balance is 100 megawatt input and there was a 102.5 megawatt output, is the difference from the electric heating or steam, or what makes up that 2.5 megawatt difference between the two?
Yeah, it's coming from that you burn part of that, the charcoal, which is included in the 102.5. That is burned on the combustion side. That is heated. Heat is transported into the gasifier and then converted into chemically bound energy. And that is why chemically you actually convert heat into chemically bound energy in the gasifier. But of course, if you look on the whole system, you need to burn something somewhere to get the heat balance. And overall, then it's around 87% if you go for the chemical efficiency.
Okay, thanks. Jim McMillan asks a good question, just always a challenge with biomass gasification. His question is, what challenges were encountered with reliable long-term feeding of solids into the gasifier?
Yeah, it was, in the beginning it was a really big problem, but in the end we solved it by actually lowering the bed inside of the gasifier. So it's not so much bed material, but heating the screw. So more or less that you have top feeding to the gasifier. The second thing was what actually made it all running in a good way was that you didn't feed back any of the ashes to the tube feeding system. In the design, you have ash returned to the gasifier at the same place where you have the fuel, and that actually catalyzes the conversion of the fuel, plugging the screw. So when you fill these two parts, lowering the bed more or less below the fuel feeding point, and also removing the ash recycling into the gasifier, it was, in the last 2 rounds, we didn't see any problem in the feeding.
Okay, thank you. Rob Williams asks if you have plans to run the 20 megawatt plant on other feedstocks, particularly forestry residues and or recovered or waste wood, which you had indicated in the slides.
Yes.
Oh, sorry. The plant was run on bark, it was run on forest residue, and it was run on waste wood as trials. The problem was with that it wasn't drier, that makes it problematic with the bark, and also that the fuel silos was not big enough during the operation to produce enough of gas with the setup it was to run the methanization. So the gasification and so on was verified for all these fuels, but it was due to other things, it was not possible to run the whole plant with the fuel to operate those for methanization. But the gas quality was met, and it was run stable when it was have a stable moisture content.
And for forest residues, if I may add, the humidity was a very important factor, and because we couldn't secure enough of dried forest residue, and we didn't have our own dryer. We could only run with forest residues intermittently. We ran it long enough to be able to produce the calculations that we have shown you, but we could not run it continuously.
Okay, thanks. Then we have a few questions relating to the biomethane itself. So Van Bush asks what the delivery pressure was of the biomethane and if the compression costs to put it into the grid were included in the production cost.
Yes, those costs are included, and the pressure when leaving the plant was around 3 bars. We compressed it to 35 bars, which is the pressure of the national grid.
Okay, good. And then the purification of that was indicated as 97%. Is that some particular standard? Why specifically 97%?
Well, actually, the specification for the national grid in Sweden is a minimum 95% of methane content. The technology from Haldor Topsøe guaranteed 96%, but in reality, we produced at 97%. So the technology was even stronger than the performance goal.
Okay, good. Fanren Ming asks if you've calculated the minimum selling price of the biomethane produced, and if if lignocellulosic feedstocks will be able to make the plant reach break even.
Yes, it's more or less good to make it break even, but it comes down to also that you need to have little investment, and also that you need to have a new permit. And when you go for waste wood feedstock, the test we shown was that it was a little tricky to get a stable delivery of it, as you needed 6 tons an hour even for this small plant. And the trial that we did was that even if we planned it for several months before and it was promised, we was only able to have a stable operation for 3 or 4 days a week. So that is a tricky part with the waste wood availability. That it's not as a forest residue anyway in Sweden that you actually get it all the time. And if you are reliant on that you only can use the waste wood, then you can run into a period where you have a problem with meeting the price level that you need. And if you look on the biomass produced, I would say around below 50 euro per megawatt hour would not be feasible at any cost, because if you start to require so much waste wood, the price for the waste wood would most likely increase. Therefore, when we do our economics, we use the forest residue because that are available on this type of scales in more at all times.
Okay. Donatella asks what the maximum number of hours of continuous operation was achieved.
It was just below 1900 hours. And as Henrik, I think, mentioned in passing, the interruption was because of a chain that broke into the feeding screw of the biomass into the gasifier.
Okay, so
it was several runs about 1,000 hours. So
okay.
The indication was that if there had been one more run, it was more likely to be more than 2,000 hours of operation that was looking for them, and even more than.
Good. Ben asks how you solved the problem of feeding solid material into a pressure vessel. And I guess to that, I would add my own question of what was the pressure sort of at the feed point in the gasifier?
At the feedstock it was maybe some kilopascal overpressure, especially then when we lowered the dead level. So actually the upper part of the screw was in the freeboard of the gasifier, where it was just some kilopascal above atmospheric. So it was more, like I said, it's still atmospheric operation. So the solve, but even then, we cannot have any nitrogen into the system. So it was a lock hopper system, which was a two-step lock hopper system that then removed all air and exchanged it with carbon dioxide. But also the carbon dioxide need to be handled with some care, because in the end it was actually lowering the carbon dioxide in the fuel feeding system and so on that actually made it possible to reach the 20 megawatt output, because otherwise you needed to have too much heat into the reboiling of the amine scrubber.
Okay, great. Baron asks how much hydrogen is allowed in the Swedish grid as part of the biomethane, or the natural gas, the synthetic natural gas.
The specification we had was a requirement of maximum 2%. That is not really the limit for the national grid. It was the limit of the compressor, of the bearings actually of the compressor, not to damage it. So it's well below that. I can't tell you the exact number, but 2% was what we had and we kept below.
Okay, good, thanks. There's a question, how long it takes from system startup to full biomethane production?
Well, in our case, it took around 2 years to reach that. The major portion was to tune the gasification. But to reach the 20 megawatt production took another year. We had to tune the various systems. The major bottleneck was the removal of tars in the tar absorbers, which is an elaborate system. But we tuned it such that we at the end had exceeded 20 megawatts.
But from a standstill to biomass production, that was approximately 1 week.
Yeah, yeah. To start up the...
To go from a food system into a system in operation, that is took approximately 1 week.
Okay, so from a cold start to when you're actually putting biomethane into the grid is about 1 week?
Yes.
Okay, good. Okay, now we've got another question. This one's a little bit longer. It says, if my calculation is correct, if I say the break-even point is 60 euros per megawatt hour for methane versus the current price of $7.2 per million BTU, this means that you're 2.5 times more expensive for the 200 megawatt plant versus the current methane price. I guess that's a question if that seems reasonable or correct.
Yeah, I would say around 2.5 current natural gas price. Yes, it is. So doing it is approximately that. Yeah.
Great. Another question from Frederick. If you had to redo it, would you do some fundamental changes in the choice of the technology, for example, the design or the type of the gasifier?
Yeah, I would say, as more or less we have indicated in the presentation, one would build the gasifier from existing type of technologies that are well commercial, that are several units out, and that is more or less what we've shown, that we can take a bubbling flue gas bed, connect it to a circulated flue gas bed, and run it more on standard technology. And that was really shown in the methanization, where you put together standard units straight over, and that it took like it was built on time, and it was taken up in operation with in less time than was planned for them. So it's just between 2 and 3 weeks it took instead of 4. And for looking at it like it's 100 reactors put together, and you take it up in 2.5 weeks. That you only do if it is well known technology.
But the major change would be to have 2 gasifiers, so that one can go down without and be maintained or cleaned without the interruption of deliveries to the grid.
And that can also be added here, that the methanization part, as designed, it could go down to 40% capacity. With some other adjustment, it may go down to 30% of the full operation, which means that you have a big flexibility in this part by adding 1 or 2 or 3 gasifiers to it. So you can actually be up and running all the time.
Okay, good. Sort of a similar question regarding now the downstream methanization part, like the scrubber technology, was costly. How would you maybe approach this in the future? Not specifically the gasifier, but the downstream component.
Yeah, if you take the scrubber, I would say that in the same way as the methanization, you should go to the petrochemical industry and look on take technologies that are there. This scrubber technology, if you look on the scrubber itself, it's used the RME due to that it should be 100% green. That was the design from the beginning. Looking on the RME, what it actually do is that it take away the naphthalene. The scrubbing is done by the tar itself, that is recirculated. The scrubber, when it has fresh RME, it doesn't make its job. But after some time, when you also have if the tar concentration in the scrubber agent increase, it takes away, it increases efficiency. So the RME is only removing the naphthalene. It's actually making it not to crystallize. And that is what the RME. And one should find some other part here. And this is one of the extremes that to take just to condense it out on the surface, which is not a metal surface. It was a silicon oxide, and we saw that it was not sticky to that one. So here we can see great improvement. If you look on the carbon bed, it was built actually as a temperature swing operation, which makes and operational and design was also expensive. If you go for a large scale, then you should most likely have some sort of regular scrubber technology for removing PTX that are available in the petrochemical industry. And then we will have the carbon bed that's guard bed. So it's coming back also to the first question. You should use technologies that are up and running in the petrochemical and refinery industry.
Okay, thanks. At what temperature does the plate and frame heat exchanger for the tars need to be operated to avoid clogging, I guess, by the heavier tars?
If you look on, at this stage, if you look on the scheme that is put up, the first part of the regular heat exchanger that we had was taking down the gas to little more than 140 degrees. Going below that, you actually start to have cool spots in the system where you have actual condensation out of water and so on, and that you don't want to have. So what you do here is that you actually get it a little together with all the particles, and then you take them away in the filter together with the limestone. Then it goes through, and that gas you actually can take on this, what we say, the heat exchanger down to ambient temperature. So, but this, to some extent, needs also to be proven. Now we have done it with one slipstream, and it's shown very promising results. And we intend to see if we can go down, maybe to send them and so on, to test it for more long time testing them.
Okay. And one more question. Did you or would you in the future look at different back-end options, for example, Fischer-Tropsch to drop in fuels instead of methanization?
When I look on, I would say that Fischer-Tropsch or other more valuable molecules would be preferable. It would be more easily to get this type of technology to fly. I would say that one should look on the gas getting out of the gasifier in the same way as one look at the refinery. You have a certain part that is created as methane. If you have a Fischer-Tropsch and you take the methane with the syngas through it, it will convert the syngas part into more valuable hydrocarbons. And then you can have the methane as a slipstream and looking on the gas more like a crude oil coming in to actually optimize the process to maximize the value of the output. But definitely, if I would go for a second generation of this, one should upgrade the syngas to more valuable, syngas part of the gas, to more valuable product than methane.
Okay, great. Thanks. Doesn't look like there are any other questions, and we've had a good question and answer period here. So I think with that, I would like to thank everybody who asked questions, and thank everybody who attended the webinar. And most importantly, I wish to thank Henrik and Freddie for an excellent presentation and discussion. And on behalf of IEA Bioenergy, I'd like to thank you all for your participation and remind you that the presentation slides and a recording of the webinar will be available on the IEA Bioenergy website in about a week or so. So if there's no other comments from Henrik and Freddie, then I thank you for the participation.
Thank you all.
Yeah, thank you all for listening.